The last blank place on the map is not shaped like a continent. It is a narrow patch of seafloor inside a trench in the South Pacific, a dark strip between two overlapping survey routes where steep walls, unstable sediment, and difficult currents have defeated one vehicle after another. On every global map around it, the ocean floor appears in extraordinary detail. Mountain chains cross the planet beneath the waves. Canyons descend from continental shelves. Volcanoes rise from abyssal plains. The scars of landslides and ancient impacts are visible. Every other deep trench has been mapped, sampled, filmed, and listened to. Only this small patch remains. Far above it, a research vessel rolls gently on a moonless sea. Inside the control room, a dozen people watch an autonomous vehicle descend through black water. The vehicle is called Orpheus 39. It carries sonar, cameras, chemical sensors, water samplers, and two delicate mechanical arms. It does not carry a person. At this depth, human presence would add risk without adding much reach. On the largest screen, the seafloor map ends in a jagged white shape. The vehicle is still 3 hours from the bottom. If the mission succeeds, the international project will announce that the deepest ocean has been fully explored. But what could those words possibly mean? They cannot mean that every liter of water has been examined. The ocean is too large and too alive for that. They cannot mean that every organism has been counted. New animals are born, old ones die, vents open, vents close, sediments move, and species travel through darkness without asking whether anyone has recorded them. They cannot mean that the ocean has no mysteries left. A map can be complete while the processes unfolding across it remain uncertain. For this thought experiment, fully explored means something more realistic and more demanding than a simple photograph. Every part of the deep seafloor has been mapped with modern high-resolution sonar. Every major trench, ridge, canyon, abyssal plain, seamount, vent field, cold seep, and unusual geological structure has been visited by instruments. Representative habitats have been filmed and sampled. Long-term observatories listen to the water, measure currents and chemistry, and watch selected ecosystems over years. The resulting data are organized, compared, and made available to researchers around the world. Humanity has not learned everything. Humanity has finally built a reliable first edition of the deepest ocean. Tonight, we are going to follow the effort that creates that first edition. It will take decades. It will begin with mapping and grow into biology, geology, climate science, archaeology, engineering, medicine, law, and conservation. It will reveal extraordinary life and very ordinary pollution. It will improve warnings without granting the power to predict every disaster. It will create valuable knowledge and dangerous opportunities at the same time. And at the center of the story will be a question that becomes harder with every discovery. How do you explore a world without becoming the force that damages it? Before the first fleet launches, the deepest ocean is still largely unknown. The deepest confirmed point lies in Challenger Deep, within the Mariana Trench in the Western Pacific. Modern measurements place it at about 10,935 meters below sea level. If Mount Everest were placed at the bottom, more than 2 kilometers of water would still cover its summit. At that depth, pressure is roughly 1,100 times the atmospheric pressure at the surface. Every square centimeter of a vehicle is pushed inward with extraordinary force. A tiny weakness in a window, cable seal, battery housing, or metal joint can become catastrophic. Human beings are not slowly squeezed by this environment. Without a pressure vessel, the body has no meaningful way to survive it. Sunlight disappears much earlier. The upper 200 meters contain most of the ocean's familiar daylight. Below that lies the twilight zone, where light weakens rapidly. Beyond roughly 1,000 meters, sunlight no longer supports vision or photosynthesis. The darkness below is not empty. It contains flashes, glows, pulses, and moving points created by living organisms. What it lacks is the daily light arriving from the sky. The deep ocean is also cold, usually only a few degrees above freezing away from hydrothermal activity. Food is limited across much of the seafloor. Most energy arrives as particles falling from above, fragments of plankton, waste, dead animals, and other organic material descending through the water column. In some places, chemical energy rises from below through vents and seeps, supporting ecosystems that do not depend directly on sunlight. The conditions are extreme, but they are not uniform. A broad abyssal plain at 4,000 meters is different from a volcanic ridge, a methane seep, an oxygen-poor basin, or a hadal trench descending beyond 6,000 meters. The phrase deep ocean hides many worlds. Human beings first reached Challenger Deep in January 1960. Jacques Picard and Don Walsh descended in the bathyscaphe Trieste, a vessel with a small pressure sphere suspended beneath a larger float. The journey down took hours. They spent only about 20 minutes on the bottom. Sediment stirred by their arrival reduced visibility, and the historical report of a flatfish at that depth was later questioned because bony fish are not believed to survive at the very deepest part of the trench. The achievement remained extraordinary. 2 people had crossed nearly 11 kilometers of water and returned. More than half a century passed before another person reached the bottom. Later expeditions brought improved cameras, sampling, and sonar. By the 2020s, repeated dives had made Challenger Deep less unreachable than it once seemed, but not ordinary. A small number of visits to one famous location could not represent a trench hundreds of kilometers long, much less the global deep ocean. Mapping was advancing faster than direct observation. Satellites could infer broad seafloor features by measuring tiny variations in sea surface height caused by gravity, but those maps were coarse. A mountain hidden underwater slightly changes the local gravitational field and pulls a small mound into the sea surface above it. That signal can reveal the presence of a large feature, yet it cannot show the fine structure needed for navigation, habitat research, cable planning, or detailed geology. High-resolution mapping requires sonar closer to the seafloor. Research ships send sound pulses downward and measure the returning echoes. Multi-beam systems cover a wide strip beneath a vessel, turning travel across the ocean into a slow process of painting the bottom with sound. Autonomous vehicles can fly closer to the seabed and reveal smaller structures, but they cover less area and require careful deployment. In April 2026, only 28.7% of the world's seafloor had been mapped to modern standards. The rest was not absent from every map. It appeared through lower-resolution satellite estimates and older soundings. What remained missing was the detail. Even mapping the entire bottom would not equal exploring it. A sonar image can reveal a cliff, mound, or crater without showing whether a coral colony grows there, whether methane escapes through the sediment, whether an ancient wreck lies half-buried nearby, or whether the feature is changing. Direct observation had covered a far smaller fraction than modern mapping. Cameras had visited selected routes, usually chosen because they were already suspected to contain something interesting. The deep ocean remained known through fragments, a vent field here, a canyon there, a few hours of footage from one trench, several cores from an abyssal plain larger than a country. The gap between map and understanding becomes the reason for the project. It begins after several events occur close together. A tsunami generated by an undersea landslide reaches a coastline faster than local models expected. The warning system works, but the model lacks detailed information about the submerged slope that failed. A damaged communications cable takes weeks to locate because the surrounding terrain is poorly mapped. A proposal for commercial extraction of mineral-rich nodules triggers an international argument because regulators possess better maps of the mineral deposits than of the ecosystems living among them. At the same time, ocean heat measurements show that deeper waters are changing in ways existing observing systems do not capture fully. None of these events proves that full exploration will solve everything. Together, they make ignorance expensive enough to become politically visible. A coalition of research agencies, universities, coastal nations, island states, private foundations, shipping organizations, and international institutions proposes a program called the Global Abyss Survey. Its public goal sounds simple: map and scientifically characterize the deep ocean within 30 years. Its internal documents are more cautious. The program will not promise to discover every species. It will not promise exact earthquake prediction. It will not promise miraculous medicines or unlimited minerals. It will create a baseline, improve models, identify vulnerable places, and build systems capable of noticing change. The distinction matters because large scientific projects often attract support by promising dramatic results. The deep ocean can easily be marketed as a vault containing cures, metals, monsters, and answers to the origin of life. Some of those possibilities are real. None is guaranteed. The people designing the survey know that public wonder may launch the project, but scientific honesty must guide it after launch. One of those people is Layla Morgan, a marine geophysicist in her early 30s when planning begins. She studies submarine landslides and the way sound reveals buried layers beneath the seafloor. Her first research cruise took place while she was still a student. She remembers standing on deck before dawn as the ship crossed a region represented on official maps by a smooth blue gradient. Hours later, multi-beam sonar revealed cliffs, terraces, and channels that had never appeared in detail before. The land had been there all along. Only the human picture had been flat. Layla joins the project because she wants the global picture to stop being flat. She also knows that maps are not neutral. The same bathymetric data that can improve tsunami models can guide mining vehicles, military submarines, fishing fleets, and cable routes. A map can protect a place or make it easier to exploit. Samir Okafor joins from a robotics laboratory. He designs autonomous underwater vehicles able to work without constant instructions. Radio waves do not travel well through seawater, and acoustic communication is slow and limited. A vehicle thousands of meters down cannot stream every decision to a human pilot. It must navigate, avoid obstacles, recognize hazards, choose survey paths, and return safely with only occasional acoustic messages. Samir's greatest concern is not whether a robot can find the bottom. It is whether the robot knows when to leave something alone. Ana Taito, a lawyer and ocean policy researcher from a Pacific island nation, joins the governing council. Her country controls a vast area of ocean relative to its land, yet has limited research ships and depends on data collected by wealthier nations. She argues that an international survey cannot repeat an old pattern in which scientific teams collect samples, publish discoveries, and leave local communities with little control over information taken from waters near them. Ana wants open maps, shared training, and rules for biological samples. She also wants some locations withheld when public coordinates could expose fragile ecosystems or cultural sites. The first argument begins before the first vehicle enters the water. Should full exploration create one completely open global database? Layla supports open bathymetry because duplicated secrecy wastes effort and leaves poorer countries dependent on whoever owns the best maps. Naval representatives object that detailed terrain data can have security value. Archaeologists warn that public rec coordinates can attract looting. Conservationists warn that a newly discovered coral garden can be destroyed by attention. Commercial partners argue that companies funding expensive surveys deserve temporary rights to use the results. The coalition reaches an uneasy compromise. General mapping data will be open. Sensitive biological and archaeological coordinates can be delayed or blurred. Raw data will be stored in several regions so that no single institution controls the archive. Samples collected beyond national jurisdiction will be registered in a shared system, with benefit-sharing rules for discoveries that later become commercially valuable. Nobody is fully satisfied. That becomes a sign that the agreement may be workable. The first fleet is not dramatic enough for global television. There is no single rocket launch and no one moment when humanity leaves the ground. Survey ships depart from different ports over several months. Autonomous surface vessels begin crossing remote waters in long parallel lines. Gliders descend and rise through the water column. Deep-towed sonar systems pass above rugged terrain. A new generation of autonomous underwater vehicles waits in reinforced hangars. The work begins with repetition. A vessel follows one line, turns, and follows the next. Sound travels down. Echoes return. Computers correct for motion, temperature, salinity, and the shape of the water column. The map gains another strip. From space, exploration looks like ships moving very slowly across an empty sea. Below them, mountains begin to appear. During the first 3 years, the Global Abyss Survey produces fewer spectacular discoveries than newspapers expect and more useful ones than most people notice. The fleet finds thousands of seamounts too small to appear clearly in older satellite-derived maps. Some are extinct volcanoes with broad, eroded summits. Others are steep cones that rise several kilometers from the abyssal plain without reaching the surface. Many contain coral, sponge, and fish communities concentrated around currents flowing over the slopes. The program finds channels carved by underwater flows carrying sediment farther than anyone expected. It finds old landslide scars along continental margins. It finds fractures, ridges, collapsed volcanic craters, and fields of small mounds formed by fluid escaping through the seabed. The ocean floor is not a smooth bowl. It is a continent-sized landscape hidden under moving water. Each feature changes something practical. A steep ridge affects currents. A canyon channels sediment. A landslide scar reveals where a slope has failed before. A seamount may shelter species found nowhere else. A rough area can threaten a cable laid according to a course map. The first major public result comes from a region where an island chain faces an offshore subduction zone. The broad tectonic boundary is already known. Earthquakes there are expected. What the new survey reveals is a network of smaller faults, sediment basins, and ancient landslide deposits layered along the continental slope. The discovery does not allow scientists to predict the next earthquake. No map can provide the exact date, time, location, and magnitude of an event that has not yet begun. The forces building along a fault remain difficult to measure in enough detail, and similar-looking systems do not always fail in similar ways. What the new data can do is improve the shape of the problem. Tsunami modelers replace a simplified underwater slope with a detailed one. They test thousands of possible earthquake ruptures and landslides. Some scenarios produce waves that arrive sooner in one bay and later in another. A low coastal plain previously treated as moderate risk turns out to focus incoming water. A neighboring harbor is partly protected by a ridge nobody had represented correctly before. Evacuation maps change. Warning messages become more specific. New pressure sensors are installed at the most useful locations. Schools practice routes that follow the actual terrain rather than the shortest road on a flat map. Several years later, a large earthquake occurs along part of the system. It is not predicted in advance. Seismic instruments detect it after rupture begins. Warning centers estimate whether the seafloor moved vertically enough to generate a tsunami. Deep ocean sensors confirm the wave. The improved map allows computers to model coastal arrival more accurately. In one town, The official evacuation route looks unnecessarily indirect. It leads away from the obvious hill, crosses a bridge, and climbs a longer road. Residents have practiced it for years because the new bathymetry showed that the nearest valley would funnel water inland. The wave arrives. The town is damaged, but the evacuation works. Afterward, headlines say that ocean exploration predicted the disaster. Layla corrects the claim in every interview. The project did not predict the earthquake. It reduced uncertainty about what might happen after one occurred. She knows the difference sounds less dramatic. She also knows that the difference saved lives. The maps improve search and recovery at sea in quieter ways. When a cargo aircraft disappears over a remote ocean, investigators no longer begin with a terrain model blurred across kilometers. Search vehicles know where ridges, trenches, and steep scarps lie. Sonar coverage can be planned without repeatedly discovering that the seafloor is more complicated than expected. Detailed bathymetry cannot guarantee that every wreck will be found. Currents carry debris. Search areas can be enormous. Deep water remains difficult, yet a complete map removes one layer of blindness. Submarine cables become part of the project as well. The cables carrying global communication cross landscapes most users never imagine. They avoid steep slopes and unstable areas when possible, but existing routes sometimes pass through poorly known terrain. The survey identifies old landslides, active sediment channels, and rough volcanic regions that can threaten future lines. Cable companies contribute mapping data collected during route surveys. In exchange, the public map helps them choose safer paths. ANA insists that the agreement include access for countries that cannot afford their own surveys. A cable crossing international waters may serve private customers, but the terrain beneath it belongs to a wider planetary system. Navies remain cautious. Some provide old bathymetric data after removing details considered sensitive. Others refuse. Researchers know that large quantities of high-quality seafloor information already exist in classified archives, collected for submarine navigation and strategic planning. The public project creates pressure to release it. A debate unfolds inside several governments. The maps could accelerate global science by years. They could also reveal survey patterns, operational priorities, and terrain useful to competitors. Some countries release processed depth data without the original acoustic records. Others contribute only areas far from strategic routes. The global map grows unevenly not because the ocean resists equally everywhere, but because human institutions reveal selectively. Layla finds this more frustrating than pressure, darkness, or storms. Machines do not pretend that a blank space is a principle. The mapping fleet faces physical danger too. A vehicle working near a trench wall is struck by a small sediment collapse. Its sonar detects the cloud too late to avoid the first debris. It loses one thruster, drops emergency ballast, and rises. Another autonomous vehicle disappears beneath polar sea ice after an acoustic beacon fails. Months later, it is found trapped against a ridge, its batteries dead, but its data intact. Every loss changes the next design. Samir's team develops vehicles that travel in groups. One maps ahead, while another maintains a safer position and acoustic contact. They learn to recognize unstable slopes, fishing lines, vent plumes, and fragile coral structures. The vehicles carry detachable data capsules that can float to the surface if the main body is lost. Autonomy improves because it has to. At first, the robots follow fixed survey lines. Later, they adjust routes when sonar reveals a feature worth closer inspection. They can circle a vent plume, map the edge of a brine pool, or keep distance from a coral colony. Machine learning systems help classify terrain and living organisms, but every automated label includes uncertainty. A pale shape may be a sponge, a mineral deposit, an abandoned fishing object, or noise. The system must be willing to say it does not know. This becomes one of the project's most important design principles. A confident error can send a sampling arm into a habitat that cannot recover. Uncertainty is not a failure of intelligence. It is information about where caution is required. By the 5th year, the mapping total passes 40%, then 50%. Progress accelerates because nations begin contributing data they already possess. Fishing vessels, research ships, ferries, cable-laying ships, and commercial survey vessels carry standardized sonar packages or donate compatible records. Autonomous surface craft cross remote areas continuously, powered partly by wind and solar energy. The ocean is still too large for speed to feel fast. A single ship can spend weeks surveying an area that looks small on a globe. Deep trenches require closer, slower passes. Ice, storms, rough terrain, marine mammals, fishing activity, and national permits interrupt routes. The map grows through accumulation rather than conquest. Public interest rises when the first major hidden mountain range is released in three-dimensional form. It is not longer than the global mid-ocean ridge, which was already known, and it is not taller than every mountain on land. Its importance lies in detail. A chain of previously unresolved seamounts appears with collapsed flanks, lava terraces, and deep channels between them. One seamount supports a forest of slow-growing corals and glass sponges. Another, only 80 kilometers away, appears almost bare. The difference cannot be explained by depth alone. Currents, food supply, rock type, oxygen, and the history of disturbance all matter. The discovery demonstrates why mapping must be followed by observation. Two shapes can look similar in sonar and contain different worlds. The biological phase expands. Research vessels deploy remotely operated vehicles connected to ships by long armored cables. Our OVS can send high-quality video and receive detailed instructions, but the cable limits range and can snag on steep terrain. Autonomous vehicles travel farther without tethers, though they must decide more for themselves and cannot transmit full video through water. The program uses both. The first systematic surveys begin at abyssal plains between 3,000 and 6,000 meters deep. These regions cover enormous areas and can appear nearly empty in photographs. Fine sediment stretches beyond the lights. A sea cucumber crosses the frame. Brittle stars raise thin arms into the current. Small crustaceans move through the upper sediment. Tracks reveal animals that passed before the camera arrived. The plain is not empty. It is sparse at the scale human eyes prefer and busy at the scale of sediment grains, microbes, and time. Food arrives from the surface in a slow fall, often called marine snow. Most organic material is consumed before it reaches the bottom. What survives supports animals adapted to scarcity. Many move slowly and grow slowly. Some reproduce only when enough food arrives. A rare event at the surface can influence life kilometers below. The survey finds that boundaries once drawn broadly across maps hide fine ecological differences. A slight change in current speed alters sediment texture. A small ridge collects food. A patch of exposed rock supports sponges and corals that cannot attach to mud. Mineral nodules create hard surfaces on an otherwise soft plain. Those nodules soon become central to the project's first political crisis. They form over millions of years, layer by layer, around small fragments such as shell pieces, rock, or shark teeth. Many contain manganese, nickel, copper, and cobalt. Across parts of the abyssal Pacific, they lie scattered like dark potatoes over the sediment. Mining companies have studied these regions for decades. They argue that metals are needed for batteries, electrical systems, and industrial development. They also argue that extracting nodules from the deep seabed may avoid some forms of land disturbance associated with mining on continents. Biologists answer that the comparison is not simple. Removing nodules removes habitat that may not return on human timescales. Collector vehicles would disturb sediment and create plumes. Noise and light would spread. The ecosystem remains too poorly understood to estimate every consequence confidently. The Global Abyss Survey was designed to provide knowledge before extraction. Now the knowledge itself increases commercial interest. A newly mapped nodule field is larger and more concentrated than expected. Nearby camera surveys reveal sponges, small corals, worms, xenophyophores, sea cucumbers, and species that have not been described. Some organisms live directly on nodules. Others inhabit the sediment around them. The coordinates are temporarily protected under the project's sensitive data rules. A commercial partner demands access, arguing that its funding helped collect the data. Conservation groups demand permanent secrecy and legal protection. Scientists want to publish. Anna argues that hiding the location forever would undermine open science, while releasing it without governance could turn discovery into a prospecting service. The dispute reaches the international body responsible for mineral activities in the seabed beyond national jurisdiction. Exploitation regulations are still under negotiation. Exploration contracts and scientific surveys exist, but commercial extraction has not begun under a completed global mining code. The new field becomes a test of whether governance can move before machinery. For 6 months, the location remains restricted. During that time, additional surveys establish an ecological baseline. Researchers map animal density, microbial activity, sediment chemistry, current patterns, and sound. They discover that one area contains a species-rich nodule habitat, while another nearby area appears less diverse but has not been sampled enough to justify that conclusion. This is the difficulty of protection under uncertainty. A blank area may be unimportant. It may also contain what nobody has yet measured. The final agreement releases the broad map, but withholds precise biological coordinates, while a protected research zone is proposed. Commercial representatives accuse the project of becoming political. Scientists respond that choosing how data are used was always political. Layla realizes that full exploration will not end arguments about the ocean. It will make the arguments more informed and more specific. That is progress, though it rarely feels peaceful. The survey continues into deeper water. The abyssal plains slope toward the trenches. At 6,000 meters, the Hadal world begins. Hadal trenches are not simply the deepest parts of a continuous slope. They are isolated basins formed where one tectonic plate bends and descends beneath another. Their steep walls, great pressure, and separation from neighboring trenches can make each one resemble an island turned upside down. Populations may become trapped within a trench system, evolving apart from relatives elsewhere. The first global Hadal campaign sends vehicles into the Mariana, Tonga, Kermadec, Japan, Kuril Kamchatka, Puerto Rico, Peru, Chile, and Java trenches, along with smaller systems that have received little direct study. The descent through a trench is not visually dramatic at every moment. For hours, the vehicle passes dark water containing drifting particles and occasional animals. Depth numbers increase. The pressure hull contracts by a tiny measurable amount. Acoustic communication takes longer to travel between vehicle and ship. At 7,000 meters, a snailfish appears in the light. Its body is pale and soft, without the heavy armor a human imagination might design for extreme pressure. Its tissues contain chemical adaptations that help proteins and cell membranes function under compression. It has no gas-filled swim bladder. It survives not by resisting the pressure with a rigid shell, but by being built so that pressure has fewer empty spaces to crush. Researchers have recorded snailfish deeper than 8,000 meters. Evidence suggests that fish may approach a biochemical limit somewhere around 8,200 to 8,400 meters. Below that, Pressure interferes with the chemistry vertebrate cells use to stabilize proteins. The deepest ocean is therefore not likely to contain a hidden population of enormous sharks. The animals found below the apparent fish limit are invertebrates, amphipods, sea cucumbers, worms, tiny crustaceans, single-celled organisms, and microbial communities. Some are fragile enough to be damaged when brought rapidly to the surface. A creature can look delicate and still be perfectly adapted to a place that would destroy a human vehicle. The survey changes how samples are handled. Older expeditions often recovered organisms in traps or cores after pressure had been lost, making behavior and physiology difficult to interpret. The new vehicles carry pressure-retaining chambers. An animal collected at 8,000 meters can be transferred into a laboratory without experiencing decompression. For the first time, researchers observe some hadal organisms alive under conditions close to their natural environment for extended periods. The results are surprising in small ways. An amphipod believed to be a general scavenger shows distinct feeding choices. A translucent sea cucumber changes direction in response to faint chemical signals. Microbes within trench sediment consume compounds at rates that shift after distant storms send fresh, organic material down submarine canyons. The trench is not sealed from the surface. It receives the consequences of weather, erosion, plankton blooms, fishing, pollution, and climate through material falling or flowing downward. One vehicle finds plastic fibers and sediment collected far below any ordinary human activity. Another films a food wrapper partly buried near the bottom of a trench. Persistent pollutants appear in animal tissue. The deepest places have not remained untouched simply because people have rarely visited them. Human influence arrived before human understanding. The discovery changes the emotional tone of the project. Public campaigns had described the hadal zone as a final wilderness. The phrase remains useful, but no longer innocent. A wilderness can be remote and contaminated at the same time. Anna argues that the survey must document pollution as carefully as new species. Some researchers worry that images of debris will overshadow the biology. She answers that choosing only beautiful discoveries would create a false ocean. The archive begins including every human object encountered: plastic, lost fishing gear, metal fragments, scientific equipment, and debris whose origin cannot be identified. Each item becomes part of the baseline. The biological discoveries accelerate. A trench in the Western Pacific contains amphipods with enzymes that remain active under pressure and cold. A South American trench contains a microbial community using chemical pathways that appear rare elsewhere. A hadal basin near a subduction zone contains unusually high concentrations of organic carbon delivered by slope failures. Most new species are not monsters. They are small variations with large scientific meaning. A worm may possess an unfamiliar partnership with bacteria. A crustacean may reproduce differently from its known relatives. A microbe may repair proteins through a mechanism never documented before. A gelatinous animal may combine transparency and bioluminescence in a way that changes assumptions about how signals travel in the dark. The public initially responds most strongly to anything large, toothed, or glowing. The project's most important biological findings often come from colorless organisms smaller than a grain of sand. One discovery begins with a patch of seafloor that looks pale in the vehicle's lights. The patch lies along a faulted slope at nearly 7,000 meters. Temperature sensors show only a slight increase. Chemical instruments detect hydrogen, methane, and reduced compounds rising through cracks. There is no towering black smoker and no obvious forest of tube worms. Samir's vehicle slows automatically because the terrain classifier cannot identify the surface. Layla requests a closer pass. The cameras reveal thin mineral chimneys only a few centimeters high, surrounded by a translucent film. Samples show that the film contains several microbial communities layered across tiny chemical gradients. Organisms near the crack use hydrogen. Others consume methane. Still others depend on products released by the layers below them. The entire system is powered largely by chemistry from rock and water rather than material falling from the sunlit ocean. Hydrothermal vents and cold seeps have been known for decades. Chemosynthetic ecosystems are not new. What makes this site important is its pressure, chemistry, and geological setting. The organisms operate through combinations of reactions not previously observed together. Some scientists call it a new type of ecosystem. Others warn that one site and a few samples are not enough. The disagreement is healthy. The first paper describes the finding more cautiously as a distinct hadal chemosynthetic community associated with low-temperature fluid flow. Popular headlines call it life without the sun at the bottom of the world. Both descriptions point toward a larger question. Could environments like this resemble places where early life emerged? Hydrothermal systems are one serious hypothesis for the origin of life, especially alkaline vents that may provide chemical gradients, mineral surfaces, and compartments capable of concentrating reactions. Other researchers favor surface pools, volcanic settings, ice, or combinations of environments. Full ocean exploration cannot travel back 4 billion years and watch life begin. What it can do is reveal how many chemical laboratories the seafloor contains. The new hadal site becomes one comparison among hundreds. Scientists analyze vent fluids, minerals, membranes, genetic systems, and energy pathways across the global dataset. They discover that vents once treated as one category are chemically diverse. Some are hot and acidic. Some are cooler and alkaline. Some are short-lived. Others persist for long periods. The life surrounding them reflects each history. The origin of life question becomes richer rather than solved. Astrobiologists pay close attention. Icy moons such as Europa and Enceladus may contain oceans beneath their crusts. If rock and water interact there, chemical energy may be available even without sunlight. The Deep Ocean Survey cannot prove that extraterrestrial life exists. It can show how life on Earth uses energy under comparable broad conditions and which chemical signatures future missions should search for. The program begins exchanging instruments and researchers with space agencies. Ocean robots test autonomous navigation under ice. Planetary scientists help design sterile sampling systems. Engineers discover that exploration in deep water and exploration on distant worlds share a central difficulty. A machine must make good decisions where direct human control is delayed or impossible. The ocean becomes a training ground for missions that may one day enter another world's sea. Medicine attracts equal attention and more commercial pressure. Marine organisms produce natural compounds for defense, communication, competition, and survival. Some marine-derived substances have already contributed to medicines, including treatments for cancer and severe pain. The new survey collects microbes, sponges, corals, and other organisms under carefully controlled permits. The resulting chemical library becomes enormous. Thousands of compounds show activity in laboratory tests. Some kill bacteria in a dish. Some affect inflammation. Some interfere with rapidly dividing cells. Some help enzymes function under cold or pressure. Almost all will fail to become medicines. A compound can be powerful and still be too toxic, too unstable, too difficult to manufacture, or ineffective in the human body. Drug development takes years of testing, modification, trials, and regulatory review. Discovering an interesting molecule is the beginning of a long path, not a cure. The project writes this warning into every public announcement. Still, several discoveries become promising. A bacterium living inside a hadal amphipod produces a molecule that attacks a resistant pathogen through an unfamiliar mechanism. A sponge-associated microbe produces a compound that protects nerve cells under certain laboratory conditions. A pressure-stable enzyme improves an industrial process used to manufacture a medicine at lower temperature. The most important early benefit may not be a dramatic new drug. It may be a tool that makes research or production better. Commercial interest raises questions about ownership. If a microorganism is collected beyond national jurisdiction, who benefits from a patent? The research team? The company that develops the compound? The country operating the ship? Humanity as a whole? Anna returns to the principle that the international seabed is treated under law as the common heritage of humankind. Biological resources do not fit perfectly into every rule written for minerals. New international agreements attempt to address genetic resources from areas beyond national jurisdiction, yet implementation remains complicated. The Global Abyss Survey creates a benefit-sharing fund. Companies receiving samples must disclose the chain of custody. If a product reaches market, part of the revenue supports conservation, open research, and scientific training in countries that contributed to the project. Critics call the system slow. Anna considers slowness preferable to discovering decades later that a shared biological resource became private property without consent. The pressure to collect more samples grows. Every organism might contain useful chemistry. Every sample also removes something from a habitat that may reproduce slowly. Samir's team develops non-destructive methods: water sampling near an organism, tiny tissue swabs, environmental DNA collected from sediment, and chemical sensors capable of detecting compounds without removing the entire animal. Cameras improve enough to measure growth and behavior across repeated visits. The project's ethical rule becomes simple to state and difficult to follow. Take the smallest amount needed to answer the question. The rule is tested during an expedition to a newly discovered cold water coral garden on a steep seamount. The corals grow in darkness, feeding on particles carried by currents rather than algae powered by sunlight. Some colonies may be centuries old. Their branches create habitat for fish, crustaceans, worms, and sponges. An autonomous vehicle is programmed to maintain distance. A current shifts unexpectedly as the vehicle turns. One thruster increases power to avoid the rock wall. The vehicle does not strike the coral, but the thruster wash breaks several branches and covers part of the colony in sediment. The damage occupies only a few square meters. The video is devastating. Researchers watch fragments fall from organisms older than the institutions exploring them. The vehicle performed within its safety rules. The rules were not protective enough. The program releases the footage instead of hiding it. Public reaction is immediate. Critics say exploration is becoming destruction. Engineers point out that the damage is tiny compared with fishing gear, mining, and other industrial activity. Conservationists answer that scientific intentions do not repair coral faster. Layla travels to the site a year later. Some sediment has cleared. Broken branches remain. Growth is too slow for meaningful recovery to be visible. The accident changes the survey. Vehicles must use lower thrust modes near fragile habitats. Standoff imaging becomes the default. Physical sampling requires independent review when a site may contain long-lived organisms. A protected buffer is created around the coral garden, and its exact coordinates are restricted. The project loses time and gains humility. Full exploration will leave traces. The honest goal is not to pretend otherwise. It is to make those traces smaller than the knowledge needed to prevent far greater harm. Years pass. The white spaces on the map continue shrinking. The number of questions grows faster. By the 12th year, the project has become too large to imagine as one expedition. It is a moving network of ships, robots, laboratories, satellites, observatories, archives, and people. Some researchers have spent their entire careers inside it. Students who watched the first survey vehicles leave port are now leading teams of their own. Layla is no longer the youngest scientist in the room. The mapping total has passed 70%. The easiest gaps are gone. What remains lies beneath persistent ice, inside politically restricted waters, along steep trench walls, and across remote areas where weather and distance make every survey expensive. The biological catalog is growing even faster than the map. New species are described, revised, combined, and separated. Environmental DNA collected from water and sediment reveals organisms never captured on camera. Genetic traces can show that something lies nearby without revealing its shape, behavior, or abundance. A sequence is not an animal. A photograph is not an ecosystem. A sample is not a population. The program begins organizing exploration around repeated questions rather than individual discoveries. Where does energy come from? How does life move between isolated habitats? How quickly do deep ecosystems recover after disturbance? How much carbon reaches the bottom? How does oxygen change with depth and circulation? Which organisms live everywhere, and which exist in one trench, vent, or seamount? The global scale finally allows patterns to emerge. Hydrothermal vent fields appear along spreading ridges, volcanic arcs, and other tectonic settings. Many had been predicted from chemistry or geology. Others were unexpected. Some release water heated above 300 degrees Celsius, remaining liquid because of the pressure. Mineral-rich fluid cools when it meets seawater and builds chimneys over time. Vent communities can be dense compared with the surrounding seafloor. Microbes use chemical reactions to create organic matter. Animals depend on those microbes directly or through food webs. Giant tube worms dominate some Pacific vents. Shrimp crowd parts of the Atlantic. Snails, mussels, crabs, worms, and other organisms form regional communities shaped by history and dispersal. Full exploration reveals that vent fields are both connected and isolated. Larvae can travel through currents between some sites. Other populations remain separated by great distances, unsuitable habitat, or water movement. When a vent stops flowing, a community can decline. New vents open elsewhere. Life must find them across darkness. Researchers compare the genetic relationships among species from hundreds of vents. The results show ancient migrations along ridges and surprising barriers across relatively short distances. A current that looks weak on a global map can determine whether a larva reaches the next habitat. This matters for conservation. Protecting one vent field may not protect a species if that field depends on larvae arriving from another. Conversely, destroying one central site could interrupt connections across a region. The project begins mapping ecological networks, not only locations. Cold seeps form another network. Methane, sulfide, and other fluids move slowly through sediments. Chemosynthetic microbes support clams, mussels, worms, and associated animals. Some seeps persist far longer than volatile vent systems. Carbonate structures grow around them. Their chemistry influences how methane is consumed before reaching the water column and atmosphere. The global survey does not discover one simple answer about whether deep-sea ecosystems store or release carbon. It discovers many pathways. Organic matter falls from the surface. Some is eaten and returned to the water as carbon dioxide. Some enter sediment. Whales carry large pulses of carbon downward when they die and sink. Methane rises through seeps and can be consumed by microbes. Hydrothermal systems transform chemicals and support biomass. Currents move dissolved carbon through basins over centuries. The deep ocean is not one reservoir with a single remaining capacity. It is a dynamic system of storage, circulation, transformation, and release. Climate scientists use the new maps and observing network to improve models of how heat and carbon move through the ocean. The ocean has absorbed more than 90% of the excess heat trapped in Earth's climate system. Much of that heat is stored below the surface, and its distribution affects sea level, circulation, marine ecosystems, and future warming. Before the survey, temperature measurements were concentrated along repeated shipping routes, research lines, and autonomous float depths that did not fully sample the deepest basins. The project adds instruments in trenches, boundary currents, polar waters, and near-rough topography where mixing is difficult to represent. The result is not a prediction of the future with perfect confidence. It is a smaller range of plausible futures. Scientists learned that some deep basins warm through pathways not captured well in older models. They identify regions where oxygen is declining and others where ventilation remains stronger. They observe how currents interact with ridges and canyons, moving heat and nutrients vertically. Coastal climate projections improve because the deep ocean is connected to ice shelves, sea level, storms, and circulation. But uncertainty remains. Human emissions, atmospheric feedbacks, ice sheet behavior, and future policy cannot be mapped with sonar. Exploration improves the physical foundation of the models. It does not decide what humanity will do with the results. A network of deep observatories becomes one of the project's most valuable creations. Some sit on tectonic boundaries, measuring ground motion, pressure, and fluid chemistry. Others monitor vents, currents, sound, carbon, and biological activity. They send information through acoustic links to surface buoys and then by satellite. The system gives the deep ocean something like a permanent medical chart. It records slow trends and rare events. One observatory captures a submarine volcanic eruption from beginning to end. Earthquakes increase. The seafloor deforms. Water chemistry changes. Lava emerges and reshapes the local terrain. A vent field is buried. Months later, microbial films appear on new rock. Mobile animals return. Larvae settle. A new community begins. For the first time, researchers watch deep sea succession across its full early sequence rather than arriving after the event and reconstructing what happened. Another observatory records a turbidity current, a dense flow of sediment racing down a submarine canyon. It snaps instruments, moves boulders, and travels hundreds of kilometers across the seafloor. The event explains how organic material, pollutants, and geological debris can reach deep basins rapidly. The ocean floor is often slow. It is not always calm. At the same time, the geological picture becomes more complete. The global mid-ocean ridge, the longest mountain system on Earth, would be mapped as one connected but varied structure rather than a line generalized across the planet. Researchers would see where plates separate smoothly, where faults offset the ridge, where magma supply rises and falls, and where volcanic construction gives way to tectonic stretching. Most of Earth's volcanic activity occurs beneath the ocean, but much of it passes without direct observation. The completed observing network would record eruptions that once left only indirect chemical or seismic signals. Scientists could compare lava shape, eruption rate, hydrothermal response, and biological recovery across different tectonic settings. They would also map subduction zones from the shallow margin into the deepest trench. The descending plate carries water, sediment, and altered rock into Earth's interior. Fluids released from that material help drive melting and volcanic arcs. Detailed imaging and sampling would improve understanding of how surface material enters deep geological cycles and eventually returns through volcanoes. This would not turn plate tectonics into a perfectly predictable machine. Earth's crust is fractured, stressed, heated, hydrated, and transformed across many scales. The completed map would show the boundaries more clearly while revealing additional complexity inside them. Some geological discoveries would matter immediately. Previously unknown submarine volcanoes near shipping routes could receive monitoring. Unstable slopes near coastal infrastructure could be included in hazard plans. Regions of active fluid flow could be protected from construction or used to guide scientific observatories. Other results would matter across generations. The survey would refine estimates of how ocean crust forms, cools, stores carbon, exchanges chemicals with seawater, and is recycled into the mantle. It would connect small mineral grains collected by a robot to the movement of entire tectonic plates. The deepest ocean would no longer be treated merely as water covering geology. It would be recognized as the place where ocean, crust, climate, and life continuously reshape one another. Acoustic monitoring reveals a second ocean layered over the visual one. Sound travels far through water. Hydrophones record whales, ships, rain, earthquakes, ice, landslides, volcanic activity, and biological signals whose sources are not immediately known. Some famous mysterious sounds from earlier decades eventually receive ordinary explanations such as ice movement, animal calls, or geological events. The survey finds new mysteries too. A repeating pulse appears seasonally across a deep basin. At first, researchers suspect machinery or an unknown whale call. Arrays show that it comes from millions of small organisms moving vertically through the water column and producing sound collectively. Another pattern changes when commercial shipping routes shift. The finding demonstrates that human noise reaches habitats far from the surface and can overlap with the frequencies animals use. The acoustic map becomes a measure of presence. It reveals migrations that cameras would never follow continuously. It identifies spawning events, whale movements, geological activity, and periods when a supposedly empty region is biologically active. Listening often causes less disturbance than lighting and sampling. The program expands passive monitoring, allowing parts of the ocean to be studied without repeated visits. Whale falls become easier to find through combined sonar, chemical sensing, and biological surveys. When a whale dies and reaches the seafloor, its body creates a concentrated source of food in an environment where large meals are rare. The process unfolds in stages. Sharks, fish, hagfish, and other scavengers consume soft tissue. Smaller organisms enrich the surrounding sediment. Later, microbes break down fats within bones and produce sulfide, supporting chemosynthetic communities. The skeleton becomes hard habitat. Specialized worms digest bone with help from symbiotic bacteria. One carcass can influence the seafloor for years or decades. Full exploration reveals that whale falls are more common than direct observations once suggested, though still scattered. Some lie along migration routes. Others occur in basins where currents concentrate remains. Not every fall supports the same community. Depth, temperature, oxygen, sediment, whale size, and local species all matter. The survey also finds large wood falls, tree trunks, and plant material carried from land into deep water. Shipworms and microbes break them down. These temporary islands may help species move between seeps, vents, and other chemically rich habitats across evolutionary time. The deep seafloor is connected by rare meals. Sediment cores provide a different kind of connection, extending downward into history. Layers of mud accumulate slowly, containing shells, dust, volcanic ash, chemical signatures, microfossils, and organic material. Researchers have studied ocean cores for many decades, but the complete map allows sampling to target basins with especially continuous records and to interpret each core within detailed surrounding terrain. Some sediments preserve climate changes across hundreds of thousands or millions of years. Ratios of oxygen isotopes in microscopic shells reflect past ice volume and temperature. Dust layers record dry periods and wind. Ash identifies eruptions. Changes in species reveal shifts in water masses and nutrients. No single core is a perfect history of Earth. Sediment can be disturbed by animals, currents, landslides, dissolution, and gaps in deposition. The global collection allows records to be compared. A climate event visible weekly in one basin appears clearly in another. An apparent global change turns out to be regional. A missing layer is recognized as erosion rather than a calm period. The seafloor becomes an archive with damaged pages, duplicates, and translations. It can be read more accurately once the shelves are mapped. Human history appears within that archive too. The project locates wrecks from modern wars, commercial accidents, migration, exploration, and older trade. Deep, cold, low oxygen conditions can preserve wood, cargo, and organic material better than shallow water in some environments. But preservation is not guaranteed. Pressure does not freeze time. Bacteria, corrosion, currents, sediment, and wood-boring organisms continue working. Some wrecks are known from records. Others have no surviving name. An ancient vessel found in a deep basin carries amphorae arranged in rows beneath collapsed timbers. The cargo links ports already known to historians, but its route crosses a region where direct trade had been debated. The discovery does not rewrite all maritime history. It provides one strong piece of evidence in a larger argument. A more recent wreck creates a difficult question. It is a war grave containing the remains of sailors. The survey vehicle discovers it during a mapping pass and records identifying features before the team understands what it has found. The footage is not released publicly. Governments, historians, and descendants are contacted. The site receives legal protection. Researchers use non-invasive methods and keep the coordinates restricted. Full exploration cannot treat every object as data without context. Some places are laboratories. Some are graves. A third wreck contains fuel and chemicals that could leak as metal corrodes. Thousands of potentially polluting wrecks from the 20th century lie across the ocean. Detailed mapping helps identify which are near vulnerable ecosystems or show signs of failure. Engineers can prioritize monitoring and, where feasible, remove or contain hazardous material. The historical discovery becomes an environmental responsibility. The project finds other evidence of human presence everywhere: trawl scars, mining tests, cables, anchors, munitions, lost containers, scientific instruments, and plastic. The completed map will not show a pristine planet. It will show the reach of human activity and the places where that reach has not yet become dominant. One of the most sobering results comes from trench sediment. Microplastics appear across samples from different oceans. Their abundance varies, but their presence is widespread. Fibers and fragments have traveled through currents, sinking particles, animal bodies, and submarine flows. The deepest point is not a sealed vault. It is downstream from the surface world. Researchers trace some pollutants through food webs. Animals consume particles directly or through prey. Persistent chemicals accumulate in tissue. The biological effects differ by substance, species, and exposure, and many remain uncertain. Full exploration makes the uncertainty impossible to ignore. It also creates a baseline against which future change can be measured. When governments negotiate plastic controls, waste systems, fishing rules, and chemical restrictions, the deep ocean data enter the debate. Pollution no longer ends at the edge of the beach in public imagination. Maps show where it settles. The survey has reached 85%. The remaining gaps are the most difficult and the most politically charged. At the same time, pressure for commercial use is growing. The commercial argument becomes sharper as the map approaches completion. By now, the survey has identified most regions containing polymetallic nodules, cobalt-rich crusts, and seafloor massive sulfide deposits at the resolution needed to plan detailed investigations. It has also identified coral gardens, sponge grounds, nursery habitats, vent communities, migratory corridors, sediment systems, and ecological connections that older resource maps barely represented. The same picture can be read in two ways. One map shows metal needed by industry. Another shows habitats that may recover over centuries, millennia, or not at all on any human timescale. The international rules governing mineral exploitation in the seabed beyond national jurisdiction have taken years to negotiate. Exploration regulations exist. Commercial extraction requires a more complete framework addressing environmental standards, financial terms, monitoring, liability, inspections, benefit sharing, closure, and what happens when damage crosses boundaries. The Global Abyss Survey does not write those rules, but its data make vague language harder to defend. How large must a protected area be? How far can a sediment plume travel? Which species depend on nodules that would be removed? How much baseline data are enough before disturbance? What level of uncertainty is acceptable when recovery may take longer than a civilization? Scientists cannot answer these questions with one number. The program can measure currents, animal density, genetic connections, noise, sediment behavior, and carbon processes. Regulators must still decide what risks society is willing to take and who is allowed to benefit. A consortium proposes the first tightly regulated extraction test using a full-scale collector in an area surveyed for more than a decade. The test is not commercial production. It is designed to measure disturbance under realistic conditions. Some researchers support it because models cannot replace every observation. Others argue that testing the machine creates momentum toward an industry before the ecological question is settled. Anna opposes approval until independent monitoring is guaranteed. She insists that the company cannot control the sensors used to judge its own impact. The final permit requires observers from several countries, public release of data, a financial bond for restoration and long-term monitoring, and automatic shutdown thresholds. The collector begins moving across the abyssal plain. It gathers nodules from a narrow test strip, separate sediment, and sends material upward through a pipe. Cameras show the immediate effect clearly. The vehicle crushes animals in its path, removes hard substrate, and leaves tracks in sediment. A plume spreads behind it. The uncertain part is how long the plume remains suspended and what happens after it settles. Models had predicted several possible ranges. Instruments show that most large particles fall relatively near the track, while finer material travels farther and remains in the water longer than the company's preferred estimate. Sediment settles across filter-feeding organisms. Noise is detectable beyond the test area. Microbial activity changes within the disturbed strip. After 1 year, the tracks remain obvious. After 5, mobile animals have returned in some numbers, but communities attached to nodules cannot return because the nodules are gone. The nodules formed over millions of years. No restoration plan can replace them within any meaningful human period. The test does not prove that all deep-sea mining is unacceptable under every condition. It proves that calling the impact temporary would be misleading. The resulting regulations become stricter. Some regions are excluded entirely because of biodiversity, ecological connectivity, or scientific value. Any future extraction must occur within limited areas, with independent observation and long-term liability. Several countries and companies decide the economics no longer justify the uncertainty. Others continue pursuing the possibility. The argument remains unresolved. Full exploration does not create unanimous policy. It makes denial more difficult. The resource maps also affect national politics. Coastal states discover mineral deposits and biological resources within their exclusive economic zones. Some see a path toward revenue and development. Others declare large protected areas. Island nations face particular pressure because they may have vast ocean responsibilities and small administrative budgets. Anna spends years arguing that ocean data should increase local power rather than merely attract outside investment. The survey funds regional laboratories, vessel time, scholarships, and data centers. Young scientists from island and coastal nations become principal investigators rather than guides attached to foreign teams. This changes the questions being asked. A distant university may prioritize globally unusual species. A local community may prioritize fish movement, coastal hazards, cultural sites, or changes affecting food. Both kinds of science matter. Full exploration becomes more complete when the people living closest to the ocean help decide what complete means. The project develops agreements for traditional knowledge as well. Navigators, fishers, and coastal communities hold observations about currents, animal behavior, weather, and seafloor hazards accumulated across generations. These observations do not replace instruments, and instruments do not make the observations irrelevant. In one region, fishers describe a place where the sea changes color and whales gather at a particular time of year. The location lies above a deep canyon that concentrates nutrients through upwelling. The survey's instruments explain some of the pattern, while historical accounts show that it has shifted over decades. The combined record is longer than either source alone. As public data expand, another conflict appears. A research group discovers that a supposedly anonymous global bathymetry dataset can be combined with shipping records, cable maps, and other open information to identify vulnerable infrastructure routes. The risk is not created by any one map. It emerges from layers. Security agencies demand that detailed maps near cables and strategic installations be removed. Open science advocates object. Once data are withdrawn for broad security reasons, governments may classify anything inconvenient. ANA proposes a tiered system. Terrain remains open. Precise infrastructure status and security-related overlays remain restricted, and independent reviewers determine whether secrecy is justified. The compromise is tested when part of the restricted archive is stolen. The breach does not reveal a hidden sea monster or secret mineral field. It reveals survey records near several cable landing corridors and naval areas, along with exact coordinates for a newly discovered archaeological site. The wreck is visited illegally before authorities can respond. Objects are removed. Sediment is disturbed. The thieves are eventually caught when they attempt to sell artifacts, but the site's original arrangement can never be fully restored. For Layla, the loss is more painful than stolen equipment. Archaeological context is information. Once objects are separated from position and surroundings, part of the story disappears. The breach forces the project to rebuild its data system. Sensitive coordinates are separated from scientific descriptions. Access is logged and reviewed. Archaeological sites receive legal protection before detailed release. Security standards become as important as pressure ratings. The event also raises a larger question. Can a planet be fully explored if some knowledge must remain partly hidden? The project answers yes, but not comfortably. Understanding can exist without universal publication of every coordinate. A complete scientific record can include protected information, provided the restrictions are narrow, accountable, and not used to erase inconvenient results. The principle is difficult to maintain in practice. Some governments classify environmental data that could reveal industrial damage. Companies claim trade secrecy over baseline surveys. Activists release coordinates to force public attention, sometimes exposing sites they hope to protect. Researchers argue over whether openness or restraint creates the greater risk. There is no final technical solution to a conflict about trust. The project survives because its archive is distributed. Copies exist under different institutions and laws. No single government or company can quietly remove the whole record. Independent scientific panels compare versions and publish changes. Redundancy protects knowledge the way multiple pressure seals protect a vehicle. Engineering continues advancing beneath the political noise. The earliest autonomous vehicles could remain at full ocean depth for limited missions before returning to a ship. Later generations recharge at seafloor docking stations or surface autonomously to transfer data. Some draw small amounts of energy from currents, temperature differences, or microbial fuel cells, though these sources cannot power every demanding instrument continuously. Navigation improves through inertial systems, terrain matching, acoustic beacons, and maps created by earlier missions. A vehicle can recognize a cliff from sonar and compare it with the global bathymetric model, much as a person might recognize a mountain skyline. Communication remains constrained by physics. Acoustic messages travel through water but carry far less information than fiber or radio through air. High-quality video usually stays on the vehicle until recovery or reaches a nearby cable. Laser communication works only across limited clear water distances. The deep ocean never becomes a place of effortless live streaming everywhere. The limits shape the science. Robots receive goals rather than continuous instructions. They decide which path is safe, when a sensor reading is unusual, and when a discovery is important enough to interrupt the planned survey. They carry ethical constraints. Do not enter protected buffers. Do not sample without authorization. Do not approach large animals beyond specified limits. And surface if uncertainty crosses a threshold. No rule covers every situation. A vehicle finds an organism attached to the only stable point where it can place a navigation beacon. It must choose between completing the network and avoiding disturbance. The machine waits and requests instruction rather than treating mission completion as the highest value. Samir calls this designed hesitation. In ordinary engineering, hesitation can sound like weakness. In exploration, it can be the behavior that preserves what has not yet been understood. The pressure housings change as well. New ceramics, titanium alloys, syntactic foams, glass spheres, seals, and manufacturing methods reduce weight and cost. Electronics are designed to tolerate pressure rather than always being enclosed in one-atmosphere containers. Batteries become safer and more energy-dense. These advances spread beyond ocean science. They improve offshore maintenance, environmental monitoring, cable repair, underwater archaeology, disaster response, and industrial inspection. Some pressure-stable enzymes and materials inspire manufacturing techniques at the surface. There are no permanent cities at the bottom of Challenger Deep. The idea remains visually appealing and scientifically unnecessary. Keeping human beings alive at full depth would require a pressure-resistant habitat, life support, emergency escape, power, food, waste management, and continuous maintenance in a place where rescue could take many hours or longer. Robots can observe more safely and for longer. Permanent presence arrives in another form. Cabled observatories operate in selected regions connected to shore. Autonomous stations sit in trenches and on ridges. Mobile vehicles return on schedules. Crewed submersibles still descend for certain missions, because human perception and decision-making can be valuable, but most exploration is performed by machines supervised from ships and laboratories. The deep ocean gains inhabitants made of metal, glass, ceramic, and code. They do not replace the life already there. Their purpose is to watch without demanding that the environment becomes suitable for humans. The most ambitious observatory is installed near a subduction zone where a trench, vent field, and active faults lie within one region. It measures pressure, seismic activity, deformation, temperature, chemistry, currents, sound, and biology. A fiber cable carries data to shore. For years, the instruments record ordinary variation. Then one morning, several sensors detect a small change in water chemistry. Seismic activity increases. A camera sees cloudy fluid emerging through a crack. The signals do not predict a major earthquake, and scientists are careful not to claim they do. Instead, They document a slow fluid event linked to movement within the fault system. The observation improves understanding of how water, pressure, and rock interact near subduction zones. It may eventually improve hazard models. It does not become a countdown clock. The public has learned enough by then to accept a result that matters without pretending it offers certainty. That may be one of the project's deepest cultural achievements. It teaches people the difference between knowing more and knowing everything. The map reaches 92%. Only the hardest regions remain. Layla is approaching 60. The young scientist who once wanted to remove every blank has become someone more cautious about what a completed map can promise. The final 8% takes almost as long as the first 50. Some gaps lie beneath permanent or seasonal ice. Ships cannot follow ordinary survey patterns safely. Autonomous vehicles must travel beneath the ice without a direct path to the surface. If navigation fails, a vehicle may be unable to return to its launch opening. The polar campaigns use networks of acoustic beacons lowered through drilled holes. Vehicles follow terrain, measure ice thickness from below, and store enough energy to search for a safe recovery point. Surface teams track them with limited signals while weather changes above. The work reveals deep channels guiding warm water toward ice shelves. It maps ridges that redirect currents and basins where water remains trapped. The findings improve models of ocean ice interaction and sea level change. They also reveal ecosystems on the underside of ice and along dark seafloor regions receiving seasonal pulses of food. The polar deep ocean is not one permanent frozen stillness. It responds to moving ice, currents, river input, algae, and climate. Other gaps lie within exclusive economic zones where governments have delayed access. Some fear that mapping will expose resources. Others worry about military security or historical claims. The coalition cannot declare full global exploration while ignoring them. ANA spends years negotiating data partnerships rather than ship routes. The agreements vary. In some places, local scientists lead surveys using equipment supplied by the project. In others, raw data remain within the country while processed scientific results enter the global archive. A few regions allow mapping but restrict biological sampling. Completeness becomes a diplomatic achievement as much as a technological one. One country refuses participation after a territorial dispute. Its deep waters form an obvious white area on the global map. Researchers can infer broad terrain from satellites and neighboring surveys, but not meet the project standard. The standoff lasts 4 years. It ends not through scientific persuasion, but after a major storm damages coastal infrastructure and the government seeks better seabed information for new cables, hazard planning, and offshore construction. The survey becomes useful enough to overcome suspicion. Local crews conduct most of the work. When the data arrive, the white region contains no legendary abyss or giant unknown animal. It contains a complex network of canyons, several seamounts, cold water corals, and a landslide deposit relevant to coastal planning. Ordinary usefulness succeeds where promises of glory did not. The remaining trench walls create a different challenge. Multi-beam sonar works best when sound reaches the bottom and returns without excessive shadow. Near vertical cliffs hide surfaces from instruments looking down. Vehicles must approach from several angles, close enough for detail and far enough for safety. Samir's laboratory develops small vehicles released in coordinated groups. They map opposite sides of a wall and compare results. If one loses navigation, the others help locate it acoustically. The vehicles are cheap enough that losing one does not end a national program, but not disposable. Every machine carries materials and batteries that should not be abandoned in a protected habitat. One group enters a narrow canyon where the walls reflect sound unpredictably. The lead vehicle reports a gap beneath an overhang. Its path planner identifies a possible passage and requests permission to enter. The human team refuses. A fully explored ocean does not require driving a robot into every hole. The passage is mapped from outside using sonar, water chemistry, and a smaller untethered probe designed to return if contact is lost. The decision produces a less detailed image. It also returns every vehicle safely. The project has learned that completeness must include limits. A map created by destroying equipment and scattering debris through caves would fail its own purpose. As the final years approach, scientists review the standard established decades earlier. Every seafloor cell has modern bathymetry at a resolution appropriate to depth. Every major geomorphic feature has been classified. Every distinct deep habitat type has been sampled in more than one region where possible. All known trenches have received systematic visual, chemical, acoustic, and biological surveys. Long-term observatories represent the major geological and ecological settings. Data are archived with uncertainty, provenance, and access rules. The standard does not require identifying every species. Taxonomy may take generations after samples are collected. It does not require knowing every behavior. Some animals appear rarely. It does not require continuous monitoring everywhere. It requires that no major region remain known only through a coarse guess. Critics call the standard too weak because unobserved details remain. Others call it impossible because the ocean changes before the survey finishes. Layla answers that every global atlas is dated the moment it is published. Continents erode. Rivers shift. Cities grow. A map is not false because the world continues. The completed ocean atlas will be a baseline with a date. Future exploration will measure change from it. The percentage reaches 97, then 98. Public celebrations become more frequent and slightly premature. Every newly completed basin is described as the final frontier until another quality review finds a strip with insufficient resolution. Survey teams discover gaps created by corrupted files, incompatible formats, and old navigation errors. The last blank is sometimes administrative rather than physical. A ship may have crossed the region years earlier, but the sonar calibration was incomplete. A vehicle may have filmed a slope without recording precise position. Data may exist on a drive whose ownership is disputed. The project creates a final audit team. Its members are less romantic than explorers and just as important. They inspect metadata, uncertainty, sensor records, processing methods, and duplicate surveys. They reject attractive maps when the underlying evidence is weak. A beautiful image is not the same as reliable knowledge. At 99.4%, the global atlas appears complete to anyone who does not know where to look. The remaining areas are narrow. Some lie along ice margins. Some are shadowed cliffs. One is the strip in the South Pacific Trench where several survey routes fail to overlap. This is the blank visible on the control room screen aboard the research vessel decades after the project began. Layla is there for the final mission. Her hair has turned silver. She moves carefully on the ship's stairs after years of rough weather and old injuries. Samir is no longer building vehicles day to day, but his students and their students designed Orpheus 39. Anna has joined from shore through a live satellite link, along with representatives from countries and institutions that carried the project. The vehicle descends. At 1,000 meters, sunlight is gone. At 4,000, it passes the depth of the broad abyssal plains. At 6,000, it enters the hadal zone. At 9,000 meters, no fish are expected and none appear. The external lights remain off during most of the descent to reduce disturbance and conserve energy. Sonar builds a picture and sound. The vehicle follows the trench wall, using the map terrain around the gap to navigate. The white shape on the global atlas begins to narrow. The control room is quieter than expected. There is no cheering. Everyone knows that the final line can still fail through weather, equipment, or data quality. Orpheus reaches the bottom near 10,200 meters. The seafloor is covered in fine sediment interrupted by exposed rock. Pressure sensors stabilize. The vehicle begins its planned route. Multi-beam sonar fills the first part of the blank. The terrain is not flat. A low ridge crosses the strip, perhaps formed by material scraped and folded during subduction. Small channels cut the slope. A fresh-looking scar suggests a recent sediment movement. The vehicle releases a temporary acoustic marker and begins a closer pass. Chemical instruments detect no venting. Cameras remain dim, using low light rather than flooding the seafloor. Amphipods gather briefly around a baited observation chamber. A sea cucumber moves across the sediment. Microbes leave no visible sign, but appear later in water and core samples. Then the terrain classifier marks an anomaly. It is not large. A field of thin mineral plates rises a few centimeters above the sediment. Between them lies a dark biological film. The geometry resembles no feature in the training archive closely enough for confident classification. The vehicle stops at a distance. Decades earlier, a robot might have approached immediately and taken a sample. Orpheus waits. The team studies sonar, currents, and video. Layla asks whether the feature must be sampled to complete the map. The geologists want material. The biologists want environmental DNA first. The engineers want to avoid the steep sediment edge beside it. They agree on a sequence. The vehicle circles without crossing the field. It collects water downstream and photographs the plates from several angles. A small sampler takes one sediment core outside the feature. Only after the preliminary data show no sign of a large fragile structure does the team authorize removal of a mineral fragment from the outer edge. The fragment is smaller than a fingernail. It contains layered manganese and iron minerals, along with microbial communities using reactions at the boundary between sediment and seawater. The site is not a new hydrothermal vent and not an unknown kingdom of giant animals. Its significance emerges later. The microbes appear to influence how metals accumulate on the plates, while the mineral surfaces shape which microbes can live there. Biology and geology are building the feature together. Similar processes have been suspected elsewhere. Here, the layers are unusually clear and active. The discovery helps explain part of how certain deep-sea mineral deposits grow and how life interacts with them. It also complicates mining arguments once again. A formation treated as inert or maybe a living structure in slow motion. On the ship, none of that is known yet. The team knows only that the final survey line is complete. Orpheus sends a compressed acoustic message. Route finished. Coverage valid. Returning. The white shape on the screen turns blue. For several seconds, nobody reacts. Layla looks at the complete map of the planet's seafloor, assembled from millions of lines, thousands of missions, and a lifetime of work. Then the room begins to applaud. The sound is not loud enough to reach the vehicle. Far below, Orpheus drops ballast and starts rising through the dark. The announcement does not say that the ocean has been solved. It says that the first complete high-resolution global seafloor atlas has passed independent review and that every major deep ocean environment has received systematic scientific survey. The difference is explained repeatedly because the phrase fully explored carries more certainty than science can honestly provide. The completed atlas is released in layers. The public layer contains global bathymetry, geological classifications, broad habitat maps, current models, observatory locations, and thousands of hours of selected imagery. Researchers can move from a mountain ridge in the Atlantic to a trench in the Pacific without crossing a blank area created by missing modern data. A controlled layer contains precise coordinates for vulnerable ecosystems, graves, rare archaeological sites, and sensitive infrastructure. Access requires justification and review. The restrictions remain controversial, but they prevent the map from becoming an instruction manual for looting or damage. The biological archive is larger than any team can finish analyzing. Specimens wait in museums and pressure laboratories. Genetic sequences wait for comparison. Video contains animals no specialist has yet examined. The formal declaration of full exploration marks the completion of systematic collection, not the completion of interpretation. Taxonomists estimate that decades of work remain. Some people find that disappointing. Layla finds it reassuring. A project capable of generating more knowledge than one generation can process has not reached an ending. It has created a beginning with better coordinates. Before considering the practical legacy, the completed atlas must correct one final misunderstanding. Fully explored does not mean fully observed forever. A vent can open after the survey vessel has left. A landslide can erase terrain. A species can move into a new basin. A coral colony can die during a heat anomaly. A whale can fall into a place where no whale fall existed the day before. Sediment can cover a wreck. Ice can retreat and expose a new pathway for water. The deep ocean is not a museum waiting to be cataloged once. It is part of a living planet. The complete survey therefore changes from a project into an observing system. Mapping ships no longer need to fill continental-sized blanks, but they return to places where change is expected. Autonomous vehicles repeat routes. Observatories are repaired and replaced. New instruments measure questions the original designers did not know to ask. The Global Atlas gains editions. The first edition shows the seafloor at the moment systematic exploration became complete. Later editions show volcanic eruptions, sediment movement, damaged habitats, new protection, warming water, and changes in life. Some regions change slowly enough that two maps decades apart appear almost identical. Others reveal that stillness was partly an illusion created by infrequent visits. The same is true of biology. New species continue to be described from old samples. Genetic methods improve and reveal that one named species contains several lineages. Other names are combined when differences prove smaller than expected. Rare animals remain difficult to understand. A camera may record one individual only once. The Global Archive can confirm that the sighting is unusual without explaining the animal's full life. Behavior remains especially mysterious. A map can show where a creature was seen. It cannot automatically reveal where it mates, how long it lives, how it navigates, what signals it perceives, or what role one brief appearance plays in a larger cycle. The deepest ocean becomes known in the way a forest can be known. The trails, streams, soils, major species, climate, and history can be mapped. That does not mean every night movement of every animal is recorded. Knowledge becomes layered rather than complete in one final sense. Physical geography is known well. Major processes are constrained better. Representative life is documented. Long-term change is observed. Individual lives remain partly hidden. That may be the most honest version of full exploration available anywhere. The first practical change appears in navigation. Ship routes do not suddenly move across trenches, but hazard charts improve. Seamounts, shoals, landslide deposits, and canyon systems are represented more accurately. Cable planners and offshore engineers can work from common terrain rather than proprietary fragments and course estimates. Search operations become more efficient because the seafloor is no longer an unknown variable. An aircraft or vessel can still disappear across an enormous area, and deep recovery remains difficult. Yet search vehicles can plan routes around known cliffs and ridges, identify likely debris traps, and compare new sonar directly with a reliable baseline. The second change appears in hazard science. Undersea faults and landslide systems are mapped in unprecedented detail. Long-term sensors reveal how some regions deform and release fluids. Tsunami models include real terrain from source to coast. Earthquakes remain unpredictable in the exact sense people usually desire. The complete map does not tell a city that a magnitude 8 event will occur on a particular morning. It improves long-term probability estimates, identifies dangerous structures, and produces better simulations after an event begins. Warnings become faster and more geographically precise in many regions. Coastal communities receive maps showing not only where water may arrive, but which roads, valleys, harbors, and seawalls will shape it. Evacuation planning becomes more local. Insurance and construction rules change. Some governments act. Others delay because accurate risk can be politically and financially uncomfortable. Knowledge does not automatically create preparedness. It removes one excuse for avoiding it. The climate observing system becomes the third major legacy. Deep currents are no longer represented mainly through sparse lines and temporary campaigns. Permanent and mobile instruments measure temperature, salinity, oxygen, carbon, nutrients, pressure, and movement across the major basins and passages. Scientists watch heat enter the deep ocean and move through it. They monitor changes near ice shelves and in bottom waters formed at high latitudes. They observe regions where oxygen declines, where carbon is buried, and where warming reaches ecosystems once considered stable. Climate models improve, especially in their representation of mixing around rough topography and the exchange between basins. Predictions still depend on uncertain future emissions and complex feedbacks. Full exploration does not reveal a fixed amount of heat or carbon the ocean can safely absorb before becoming full. The ocean is not a passive container. It responds. Warming changes density and circulation. Acidification changes chemistry. Oxygen loss changes habitat. Ice melt changes salinity. Ecosystems alter carbon pathways. The complete baseline makes these responses easier to measure and harder to ignore. A fourth legacy is biological. The deep ocean turns out to contain more regional uniqueness than broad maps once suggested. Some species occupy wide depth ranges and multiple oceans. Others live within one trench, one vent province, or one seamount chain. Microbial diversity exceeds anything visible through cameras. The survey does not produce a final count of species on Earth. Definitions of microbial species remain complicated. Rare organisms are easy to miss. Genetic analysis continues discovering hidden lineages within samples thought to represent one species. What changes is the scale of uncertainty. Instead of guessing from a few expeditions, biologists can estimate diversity from structured global sampling. They can identify where undiscovered species are most likely, which habitats contribute most to uniqueness, and which regions are poorly represented even within a complete baseline. Conservation becomes more precise and more difficult. Some protected areas are expanded because the map reveals ecological connections crossing their boundaries. New reserves protect vent provinces, coral gardens, hadal communities, spawning sites, and migration routes. Other areas lose proposed protection when detailed surveys show that their assumed uniqueness was overstated. This creates conflict. Conservation groups fear that precision will be used to protect only small islands of habitat while permitting disturbance everywhere else. Industry argues that broad restrictions written under uncertainty should be revised when better information exists. Ecologists warn that a place can appear ordinary and still perform an important function. A sediment plain may connect populations, store carbon, or support processes not obvious from visible animal counts. The completed survey makes protection evidence-based. It does not make value judgments disappear. Deep-sea mining remains the clearest example. The map identifies areas where ecological risk appears especially high and areas where baseline diversity seems lower. Yet lower measured diversity does not mean no value, and mineral removal remains effectively permanent on human timescales. Some countries establish long moratoriums. Others approve limited extraction under strict monitoring. Market changes reduce demand for certain seabed metals as battery chemistry, recycling, and land-based supply evolve. Several projects never become economically viable. The feared global rush does not occur in one uniform wave. Instead, decisions unfold unevenly and remain contested. The exploration program's greatest contribution is not proving that mining must happen or must never happen. It is preventing ignorance from being presented as evidence of safety. Medicine produces a handful of successes and thousands of quiet failures. The hadobacterial compound active against resistant pathogens becomes the basis for a research program. Chemists simplify its structure and reduce toxicity. After many years, a related molecule enters clinical trials. It works for a narrow group of infections rather than becoming a universal antibiotic. The pressure-stable enzyme becomes commercially useful much sooner. It allows a manufacturing reaction to run with less energy and fewer unwanted byproducts. Another enzyme improves cold water industrial cleaning. A deep-sea protein becomes a tool for studying how cells respond to stress. These are valuable results. None resembles a treasure chest opened overnight. The medical legacy demonstrates why ecosystems should not be valued only for products. Most organisms never lead to a patent. They still possess evolutionary history, ecological relationships, and intrinsic existence that do not require usefulness to humans. Archaeology changes public imagination in a different way. The completed wreck database reveals maritime history as a global network of trade, migration, labor, warfare, fishing, and loss. Some discoveries confirm written records. Others recover stories absent from official archives. Small merchant vessels, refugee boats, local fishing craft, and ships whose crews left no surviving documents. Museums build exhibitions with descendants and source communities. Three-dimensional models allow people to study wrecks without repeated physical visits. Human remains are treated under ethical and legal agreements rather than as curiosities. The ocean floor becomes a historical landscape. It is not emptied of mystery, but fewer lives vanish without a place on the map. The technological legacy spreads widely. Autonomous underwater systems inspect bridges, dams, pipelines, wind farms, cables, and ships. Pressure-tolerant electronics reduce costs. Acoustic navigation improves emergency response. Robotic systems designed to hesitate near uncertain habitats influence machines used in forests, mines, ruins, and other sensitive environments. Designed hesitation becomes a broader engineering idea. A system should not treat uncertainty as permission to continue. It should sometimes pause, gather more information, or request help. Samir considers that lesson more important than any one vehicle. Public culture changes as well. Children grow up with detailed maps of the seabed in classrooms. They learn that the mid-ocean ridge is a planet-spanning mountain system, that trenches are biologically distinct, and that the deep ocean is not a featureless dark container beneath the interesting surface. Live feeds from observatories become part of education. A class can watch a vent community, hear whale calls, follow a deep current, or compare a coral garden across decades. The images are often slow. A camera may show sediment and one moving animal for an hour. The slowness becomes part of the attraction. Not every natural system performs on demand. Tourism does not move to the deepest trenches in large numbers. Full-depth crude dives remain expensive and risky. Most people encounter the deep ocean through immersive displays, public data, museums, films, and remote participation in scientific missions. The project resists turning precise locations into adventure destinations. Fragile sites cannot support crowds merely because engineering makes visits possible. The world has seen what attention can do to accessible wilderness. The deepest habitats receive the chance to be known without becoming busy. The completed survey also changes the old comparison with space. People once said that Mars was mapped better than Earth's ocean floor. By the end of the project, that statement is no longer true in the same way. Earth possesses a detailed global seafloor map, and many deep habitats have been visited directly. Yet the comparison does not become a competition. Space and ocean exploration helped each other. Autonomous systems developed for trenches inform planetary missions. Sterile sampling methods move in both directions. Ocean worlds beyond Earth become more scientifically approachable because researchers understand a wider range of chemistry and life on their own planet. The two frontiers reveal different forms of distance. Mars is far through space. Challenger Deep is close in kilometers and separated by pressure, darkness, and water. Both require machines, patience, and the willingness to send questions where human bodies cannot remain easily. The deep ocean remains the frontier most directly connected to daily life. It regulates climate, supports food webs, carries cables, stores history, shapes coastlines, and contains the consequences of activity on land. Understanding it changes how humanity imagines the surface. A plastic fragment thrown away in a city is no longer mentally separated from a trench. Heat released into the climate system is no longer treated as something held only in the atmosphere. A coastal fault is no longer a line ending at the water's edge. A battery material is no longer an abstract commodity without a habitat attached. The complete map connects actions to places. That connection can create responsibility. It can also create new opportunities for control. Governments use the observing network to enforce protected areas and monitor illegal fishing or dumping. Companies use it to plan cables, energy projects, and resource exploration. Scientists use it to track climate and ecosystems. Military institutions use terrain and acoustic knowledge for navigation and surveillance. No discovery removes power from the ocean. It redistributes power among people who can use the discovery. Anna's final work before leaving the governing council is a charter for the Atlas. The document states that deep ocean knowledge should be maintained as a shared public good, with necessary protections for safety, culture, and fragile habitats. It requires transparent changes, independent scientific review, long-term access, and support for countries lacking expensive infrastructure. The Charter cannot force every nation to behave well. It establishes a standard against which secrecy and exploitation can be judged. Anna knows that future generations will revise it. She considers that a strength. Governance, like mapping, must be updated when the world changes. Samir's final contribution is smaller and more personal. He visits a laboratory where one of the newest vehicles is being tested. The machine is descended from Orpheus 39, but is lighter, quieter, and capable of months at sea. A student shows him its decision system. When the vehicle encounters an unknown biological structure, it maps from a distance, checks protected area rules, measures currents, and requests permission before approaching. Samir asks what happens if communication fails. The student answers that the vehicle waits or leaves. He smiles. The machine has inherited caution. Layla retires from daily project leadership after the completed atlas is released. She continues reviewing papers and advising younger teams. Her office contains an image of the first map strip she helped collect as a student and the final global map printed across an entire wall. The two images contain the same ocean. One shows how little she knew. The other shows how much remains. A journalist asks whether she feels disappointed that full exploration did not reveal a giant unknown predator, an underwater civilization, or one discovery that changes everything. Layla says the ocean changed everything many times. It revealed ecosystems independent of sunlight, though those were discovered before the global survey began. It showed how life crosses pressure, cold, scarcity, and isolation. It improved understanding of climate, tectonics, evolution, chemistry, and planetary habitability. It exposed pollution in the most remote trenches. It showed that mineral deposits can also be habitats. It preserved human stories and forced new ethical rules. The problem is not that the discoveries were too small. The problem is that people are trained to recognize transformation only when it arrives as spectacle. The completed exploration changes the world through thousands of corrections. A coastline receives a better warning map. A medicine gains a new molecule. A damaged habitat receives protection. A child sees Earth differently. An engineer designs a machine that knows when not to touch. A government can no longer claim that a blank map proves nothing lives there. No single correction becomes the entire story. Together, they form a new relationship with most of the planet. Layla returns to sea one final time several years after the Atlas is declared complete. The voyage is not ceremonial. A long-term observatory in the Mariana Trench has stopped transmitting, and a vehicle must inspect the cable. The ship crosses water that looks no different from the water she first saw as a student. Waves rise and fall. Flying fish scatter from the bow. Clouds build on the horizon. Nothing on the surface reveals the completed map below. The repair vehicle descends using terrain known in extraordinary detail. It follows a canyon wall, passes a field of sediment ripples, and reaches the observatory. A connector has failed. The machine replaces it, tests the instruments, and begins returning. The mission is routine. That is what amazes her. A place once reachable only through historic acts of courage has become part of a maintained scientific system. Not safe, not easy, and not ordinary in any physical sense, but visited through technology reliable enough that the purpose of the mission is maintenance rather than first contact. On the return route, the vehicle's camera records a translucent animal drifting above the seafloor. It is only a few centimeters long. Thin lines of light travel along its body. The classification system offers 3 possible groups and low confidence. The vehicle does not collect it. The animal passes out of the lights. Back on shore, specialists examine the recording. Some think it is a juvenile form of a known species. Others suspect something undescribed. The video is added to the archive with its uncertainty intact. The completed ocean has produced another question. Layla is pleased. If full exploration had removed mystery completely, the ocean would have become smaller in the human mind than it truly is. Instead, mystery has changed shape. Before the survey, mystery came from absence. Nobody knew what terrain occupied most of the map or which habitats might be there. After the survey, mystery comes from depth of understanding. Researchers know where the trenches are, what major systems they contain, how currents connect them, and which questions remain. The unknown is no longer a blank, white area. It is a pattern visible enough to investigate. This is what humanity would gain if the deepest part of the ocean were fully explored. A complete map of the hidden majority of Earth's surface. A global baseline for detecting change. Better models of tsunamis, currents, climate, and seafloor processes. More effective search, navigation, cable planning, and hazard preparation. Thousands of newly described organisms and many more awaiting study. New chemical tools and a small number of medical possibilities, reached through long, careful development rather than instant miracles. A fuller archive of human history. Evidence of pollution and disturbance in places once imagined untouched. Clearer grounds for conservation. Clearer targets for exploitation. New engineering capable of working under extreme pressure. And a more mature understanding of what exploration actually means. It does not mean planting a flag. It does not mean turning every place into a destination. It does not mean collecting every organism or extracting every useful object. It means observing carefully enough to replace assumptions with evidence. It means returning often enough to notice change. It means recording uncertainty rather than hiding it. And it means learning that the right to reach a place is not automatically the right to alter it. Would full exploration discover something enormous and terrifying? Probably not in the form popular imagination expects. The deep ocean may still contain large animals rarely observed, especially squid and wide-ranging species that avoid vehicles. But an ecosystem cannot hide an unlimited population of giant predators without leaving traces through food demand, genetics, carcasses, environmental DNA, and interactions with known life. A surviving megalodon would not be waiting in Challenger Deep. The animal was adapted to productive marine ecosystems and required large prey. Fossil evidence places its extinction millions of years in the past. The deepest trenches are cold, food-limited, and beyond the known pressure range of fish. The truly surprising discoveries would more likely be unfamiliar metabolisms, symbioses, life cycles, materials, and ecological connections. Science often becomes more astonishing when it stops demanding that astonishment be large. Would full exploration reveal the origin of life? It might reveal environments and reactions that strengthen or weaken particular hypotheses. It could show how mineral surfaces organize chemistry, how membranes behave under pressure, how microbes use rock-derived energy, and how vent systems vary. It would not recover the first organism or prove one birthplace beyond all alternatives. The origin of life is a historical event whose earliest evidence has been transformed by billions of years of geology and evolution. The ocean could provide clues powerful enough to reshape the debate. Clues are not a recording. Would it allow scientists to predict earthquakes? No. Detailed seafloor maps, fault geometry, deformation sensors, and geological histories would improve hazard estimates and tsunami modeling. They might reveal patterns that eventually lead to better forecasts in limited contexts. The exact prediction of major earthquakes would remain beyond what the map alone can provide. Full exploration would protect coastal communities by improving preparation, not by granting perfect warning. Would it solve climate change? No. It would improve knowledge of where heat and carbon move, how deep circulation changes, how oxygen and ecosystems respond, and how the ocean interacts with ice and atmosphere. That knowledge could improve policy. It could not substitute for policy. The ocean has buffered much of human-caused warming by absorbing excess heat and carbon. That service carries consequences: warming, expansion, acidification, oxygen change, and ecological stress. Understanding the buffer does not make endless pressure safe. Would it make the ocean richer? It would make the ocean's value more visible. Some of that value can become medicine, safer infrastructure, food security, and scientific technology. Much of it cannot be translated honestly into money. A trench species with no commercial use is still the result of millions of years of evolution. A coral garden does not need to become a drug or tourist attraction to matter. The completed map would force humanity to decide whether knowledge expands protection or merely expands access. That decision would remain open after every vehicle returns. The deepest consequence may be philosophical. For most of history, humans lived on a planet whose visible land could be crossed, but whose submerged surface remained abstract. Maps colored the ocean blue and left its relief faint. The sea appeared as the space between continents. Full exploration would reverse that image. Continents would become high regions rising from a continuous planetary landscape. Mountain chains would extend beneath water. Canyons would connect rivers to abyssal plains. Volcanoes, trenches, ridges, shelves, and basins would form one Earth. The ocean would no longer look like emptiness around the land. The land would look like islands within the ocean planet. That perspective could change how boundaries feel. Currents ignore political lines. Whale migrations cross jurisdictions. Pollution moves. Heat moves. Larvae move. Sound moves. A decision made near one coast can arrive in another country's water or settle in a trench far away. The completed survey would make connection physically visible. Not all societies would respond with cooperation. But nobody could claim the systems were separate because the map failed to show the link. Years after retirement, Layla keeps a small printed globe in her home. It is unusual because the seafloor relief is raised as clearly as the continents. Her fingers can follow the mid-ocean ridge around the planet, trace a canyon away from a coast, and find the narrow trench where Orpheus completed the final line. The globe does not contain the chemical films, animal movements, sound, pressure, cold, or darkness. It is only a model. It is enough to remind her of scale. On some evenings, she turns it slowly and thinks about how the project began with the desire to remove blanks. Over time, the work taught her that blankness had protected the ocean in one sense and endangered it in another. What people did not know, they could overlook. What people came to know, they could protect or exploit. Exploration never made that choice for them. It only made the choice harder to pretend they were not making. Tonight, imagine holding that completed globe. Let the familiar continents rise beneath your fingers. Then follow the slopes downward, past the continental shelf, the canyons, the broad abyssal plain, and the long volcanic ridges. Continue toward a trench where one plate bends into the earth. The water above it becomes darker. Sunlight fades. The temperature falls. Pressure increases steadily and without drama, held back only by the imagined shell around you. At 1,000 meters, the last sunlight is gone. At 4,000, the plain stretches beyond view. At 6,000, the trench begins. At 8,000 meters, fish approach the known biochemical limit of their range. Below that, smaller lives continue. An amphipod moves across sediment. A sea cucumber feeds slowly. Microbes work between mineral grains. Far away, a whale call travels through water. Nothing down there knows that a map has been completed. The organisms do not become more real because humans have named them. The ridge does not become taller because sonar measured it. The trench was deep before any number existed. Exploration changes the human world. The ocean continues being itself. That may be the calmest truth at the center of the whole question. The deepest part of the planet does not wait impatiently to be discovered. It does not need applause when the final survey line closes. It does not hurry because a research budget has a deadline. It moves according to currents, chemistry, geology, hunger, reproduction, and time. The project that fully explores it succeeds only when it learns to move more like the place it studies. Carefully, repeatedly, without assuming that speed is the same as progress. The complete atlas is not a conquest. It is an introduction. And now that introduction can rest where it belongs, on shelves, servers, observatories, and the minds of people who will continue the work tomorrow. You do not need to follow the vehicle back to the surface. You can remain for a moment in the imagined darkness, protected from pressure, watching the small circle of light fade. Beyond it lies a world no longer blank and never fully exhausted. The map is complete. The questions are alive. Above the trench, 11 kilometers of water rise toward the surface. The layers become lighter one by one. The pressure eases. Far overhead, waves move beneath the night sky. A research vessel continues its slow route. Someone in a control room watches instruments. Someone else has finished a shift and gone to sleep. The observatories keep listening without needing your attention. The currents keep moving. The deep ocean keeps its own time. So let the map close for tonight. Let the last sonar line fade from the screen. Let the lights of the vehicle become smaller until they are one distant point, like a star seen through dark water. There is nothing left for you to classify, measure, protect, or understand before morning. The ocean can remain vast without being held in your thoughts. Your breathing can find a slower current. Your body can settle into the surface beneath it. And while the deepest part of the planet continues quietly below, fully explored and still full of life, allow your own day to become still. Sleep well.